Welcome to Maths with EJD. In this video, I'll be talking about numerical integration with Simpson's rule. That's broadly on the numerical differentiation and integration. Previously, we had seen methods for numerical differentiation, talking about finite differences and finite difference operators. And talking about numerical integration, we had considered, um, you know, um, for numerical integration. In the previous video, I had talked about the trapezoidal rule. Then now we'll be looking at the Simpson's rule. Simpson's rule. Then there's also going to be a talk about adaptive quadrature. Okay. So again, this is done. This is next. I'll be going for this later. So the focus right now is on Simpson's rule. Simpson's rule. Hey, Simpson's rule is a method for approximating the integral of a function, particularly when the exact integral, when the exact integral is difficult or impossible to calculate analytically. Okay. Now, it is more accurate. It is a more accurate method. It is a more, it is a more accurate method than the trapezoidal rule. And it works by approximating the integrand. So the integrand is the function. The integrand is the function to be integrated. So it approximates the integrand with a quadratic polynomial. Okay. So the formula for Simpson's rule is as follows. We have the integral from a to b of f of x dx approximately equal to b minus a over 6, just like the other for the other one we talked about h over 2 or something like that. So b minus a over 6 into f of a, that's this a the lower limit, the function of the lower limit plus 4 f of a plus 4 into f of a plus b over 2, then plus f of b itself. That's the upper limit. So that is the formula for uh, Simpson's rule. Now, where A and B are the limits of integration, they are the limits of integration. Then we have f of x itself. F of x is the function to be integrated as the integrand, the function to be integrated, otherwise known as the integrand. Then we have a plus b divided by 2, a plus b over 2 is the midpoint, between a and b, midpoint between a and b. Okay. Well, with that in place, we have to also talk about generalization for even subintervals. Okay. Now let's go for this generalization. Generalization for even subintervals. So we have to take care of whether the subinterval is even or odd. Okay. So for a more general case, where we divide the interval a comma b into n equal intervals, n equal subintervals, that is, where n must be even, Simpson's rule is given by integral from a to b of f of x dx, which is approximately the same thing as h over 3 into f of x naught. So x naught is the first value in the interval, which is more or less a, f of x naught plus 4 summation from I equals 1 and all the other odd numbers up to n minus 1, where of f of xi, then plus, so it's 4 into odd, then we have 2 into summation from I equals 2 and other even numbers up to n minus 2 for the f of xi that match that. This is I now. So finally, we now have plus f of xn. That's the last sub interval. So now this is the most appropriate expression we use, if we have to divide into sub intervals. Again, we need to understand what each component is about. First of all, we have h, which is equal to b minus a over n. H is b minus a. H is b minus a over n. And that is the width of each subinterval, that you can see as the step size like we had for trapezoidal rule. So that's the step size. Then you have x naught. X naught is actually a, okay? And then you have all the others, x1, x2, and so on and so forth, up to xn, which is equal to b. They are the sample point. These are the sample points. These are the sample points. With that out of the way, let's look at an example. Let me go for this. Let's look at an example. Let's approximate the integral That's integral from 0 to 2 of x squared plus 1 dx. So our integrand here is from 0 to 2. So we go for the solution, which is this solution. And the first step in the solution would be to choose an even number or number of subintervals. Choose an even number of subintervals. So if we have to do this, uh, let's take it out. Let's divide. Let's divide the interval, the closed interval, 0, 2 into n equals to subintervals. Into n equals to subintervals. This is actually the simplest case. This is the simplest case. So we either divide it into 2 or 4. So this is the simplest case for Simpson's rule. So going by that now, we have that A is equal to 0, B is equal to 2, and N is equal to 2 also. So in that case, H will just be B minus A over N. That is 2 minus 0 divided by 2. And that is 2 over 2. That is 1. So H is simply 1. So H is equal to 1 now, in addition to the other things. So that takes care of the first step. And then we move on to step 2. Step 2. So in step 2, we compute values. Compute the values of f of x at the relevant points. At the relevant points. So we have So now we have f of x equals x squared plus 1, which is the integrand. So since we are dividing this, so since our step size is 1, so we start from 0, right? So we have the first one, which is f of x naught, and that is our f of a. A is 0, so we have f of 0, which is 0 squared plus 1, and that is simply 1. Okay, so next we have f of x1. So f of x1 will be f of 0 plus 1, that's f of 1. So we have 1 squared plus 1, and that gives us 2 simply. Then we have f of x2. So that means if you add 1 to this again, that is f of 2. We have just 0, 1, 2. So that means we have 2 squared plus 1, which gives 5. So we have the functions as 1, 2, 5. 1, 2, 5. So with that in place, we can go ahead and apply the Simpson's rule. So apply step 3, apply Simpson's rule. Simpson's rule. Okay. So apply Simpson's rule. So again, we have integral from 0 to 2 of x squared plus 1 dx to be approximately the same as 1 over 3. Our h now is 1, so that's 1 over 3 into f of 0 plus 4 f of 1. That's the odd number now. If you look at this, 4 times the odd, right? 4 times the odd, 2 times the even. So if we add more odd values, then we'll impute that. So we have 4 of f1 plus, since we don't have anything in between, we just say f2 straight. But if we have other values in between, then we'll say 2 of even. So this is f of 2 directly, and that goes. So if for instance, we had like f of 0, f of 1, f of 2, f of 3, f of 4. 1, 2, 3, 4, let's say f of 5, and then say f of 6. So it means this is going to stay apart, and then this is odd. This is also odd. Oh, 0, f of 0, f of 1, right? Oh, okay, yeah, that's fine. So that's f of 1 is odd, f of 3 is odd, f of 5 is also odd. So I'm going to say 4 into f of 1 plus f of 3 plus f of 5. Then f of 2 and f of 4 are even. So we say 2 into f of 2 plus f of 4. Okay. So, but here we just have three things. So we have the beginning and the end, and then we have only one odd thing, which is f of 1. So with that in place now, we can go ahead and compute the result. So now we are saying that integral from 0 to 2 of x squared plus 1 dx is approximately actually 1 over 3 into f of 0. We got that there to be 1. So that is 1 plus 4 into f of 1. F of 1 is 2 plus f of 2, which is the last one, and that is simply 5. So we have 5 right here. So integral from 0 to 2 of x squared plus 1 dx is approximately 1 over 3 into 1 plus 8 plus 5. 1 plus 8 plus 5. So that means we have this 1 over 3 into 9 plus 5, 14, I think. Yeah, that's 14. So that this is approximately 14 over 3, which is equal to 4.67. Okay, so we can say thus the approximate value, the approximate value of the integral is 4.67. Okay, that's what we have there. So can we compare that with the exact value? Let's look at the exact value. Okay, let me go here. So if you check with the exact value, so we have integral from 0 to 2 of x squared. Normally, numerical application is best for things that cannot be easily integrated, but we use things that can be easily integrated so we can see how efficient numerical method is. So here, if you integrate x squared, you get x squared x cubed over 3 rather, you get x cubed over 3 when you integrate x squared. And when you integrate 1, you get x. And that is from 0 to 2, right? That is equal to, this is how I like to do mine. I like to split them apart. This is like 1 over 3 x cubed from 0 to 2 plus x from 0 to 2. I like to handle it this way more efficiently. So 1 over 3 can come out. So you have 1 over 3 x cubed from 0 to 2 plus x from 0 to 2. So that is equal to 1 over 3 into, when you put 2 into x, you have 2 raised by 3 minus 0 minus 0 raised by 3 plus 2 into x, you have 2 minus 0 like this. So this is 1 over 3 into 8 minus 0 plus 2 minus 0. Okay, just taking a lot of time there. So we have 8 over 3 plus 2 over 1. 2 over 1 is obviously 6 over 3. That's everything together is 14 over 3. And you can see that looks like what we already have here, right? So you can see this is really close. So this is approximately 4.67. So in this case, right? In this case, Simpson's rule gives us the exact value, gives us the exact value because the function is a simple quadratic, is a simple quadratic. And Simpson's rule is exact for polynomials. Simpson's rule is exact for polynomials of degree 3 or less. So degree 3 or less, you get exact value. So in conclusion, we see that Simpson's rule provides a highly effective method for numerical integration, especially when the function is smooth and polynomial-like. The accuracy increases with more subintervals, and it performs particularly well for functions with well-behaved curvature. That's the conclusion right there. And of course, my style, I'd like to show you the Python code in case, the step, it can be quite a lot. But if you have the code, you can easily work with that. So imagine here now, uh, we are looking at the Simpson's rule for integral from 0 to 2 of x squared plus 1 dx with n equals 2. So, okay, I like to show the views, show line numbers so I can make easy reference. So we start with a function, we define the Simpson's rule, you define the function, you define the lower limits, upper limits, and the number of subintervals, right? So if n divided by 2 is equal to 0, so because n must be an even number, so we have to put this condition in line 3. Then in line 6, we define the step size. In line 7, we set the starting point where x is equal to it. That's actually properly x naught, but for the sake of programming, we have that. And we evaluate the function at the endpoints. So you have the result, which is f of a plus f of b. At the endpoint, that's just half into both of them. So then you sum the terms for odd indices with a weight of 4 for 1 in range 1 n over 2. So here now you just have x equals a plus ih, that's step size. And then the result is 4 times f of x. That's for the odd. Then you have 2 times f of x for the even. The result, you have h over 3. Whatever result you have, you multiply by h over 3, and that keeps going. You get that result and save it. Then in line 28, you now define the function you are differentiating. That's x squared plus 1 in this particular situation. So a is 0 lower limit, b is 2 upper limit, n is 2. That's number of subintervals, which must be even, as we know. So if you run this, you get in one blow, you just get your 4.6666 like that. So, there we go, 4.67. So this is very good. Now I intentionally put this because when we did trapezoidal rule, we integrated x squared dx with n equals 4. So in the code, I also tried to put the result for trapezoidal, which we got as 2.75. Now you see that Simpson's rule gets the exact result, 2.67, while you remember the trapezoidal rule gave us 2.75. So, and the actual value of the integral is actually it should actually be 2.67. I mean, to two decimal places, it is 2.67. That's 2.66666 and all that. So you see that Simpson's rule is more efficient than trapezoidal rule, and that's how that works. So with that, we come to the end of this. Let me see. I think a practice question would make a lot of sense here. Okay, so let's go for a practice question. Practice question. I think there was a question I did using. Okay, I guess I want to give the same question I gave for the trapezoidal rule. If you remember, that's at the very end of trapezoidal rule. Yeah, I like to give the same thing so you can compare the accuracy. Good. So f of x equals root x plus 3 over x squared plus 7. Okay, I think I will just project this, right? Let me just project this so I don't have to go back there. So it's practice question for sure. Although this is now under Simpson's rule. So approximate the integral of f of x equals square root of x plus 3 over x squared plus 7 over the interval 2, 5 using the trapezoidal rule. So now it has to be using the, okay, let me just cross this. Now, using Simpson's rule, okay? Using Simpson's rule. Now, here, it's you have to be sure. Your n, you have to decide your n because you need a even number of n. So you can choose your n to be 2 or 4 or 6 or something. Can I set it? Let me just say, for better accuracy, let me say using n, okay, using Simpson's rule with, say, n is equal to 6. Like you need 6 intervals from 2 to 5. So that can guide you. So in that case, now you're going to have like, so, your x naught, which is equal to a, is 2 now. So then you have your xn, which is 5. So you're going to have, of course, you're going to have h to be 5 minus 2 all over 6. That is 3 over 6, which is 0.5. So you're going to have 2 and then f of x1. So you're going to have f of x naught, which is f of 2. You're going to have f of x1, which is f of 2.5. So you have f of x2, f of x3, f of x4, 1, 2, 1, 2, 3, 4. And you're going to have f of x5 and f of x6. Okay. So that's 1, 2, 3, 4, 5, 6. So, so you're going to have this one and this one, they are the end values. Then the odd ones, I'll just write. So for odd, this is odd, and this is odd. So you're going to have 4 times all that, and you have the even. This is even, and this is even. So you're going to have 2 times the sum of those. So that's how that's going to be. So just walk around that and let's see what you get. Let's see what you get. So of course, we already know that the Simpson's rule is better. All right, we already know Simpson's rule is better. So do use trapezoidal rule and Simpson's rule to solve the same problem and see how accurate it can be. The exact solution may not be that easy to come by, or if you can get the exact solution, so try that. Okay. All right, so that's how it's been on this one, talking about numerical integration using Simpson's rule, which is better than trapezoidal rule. So solve this and let me see your answer in the comment section, whether on YouTube or Facebook. You're also going to see the code on Facebook. You can't see, you won't be able to see it on YouTube because I'm not able to post the code there because of some special characters in the code. I wonder why that is. But if you follow me on Facebook, you're going to see that right there. So you can copy out the code and try it out. Okay. So with that said, don't forget to sign up to subscribe to the channel and hit the notification button so that you can always get alerted each time a new video is released. Let me also know how helpful these videos are for you. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.